In this video lesson, we are going to learn about isotopes and average atomic mass. Average atomic mass is the number that can be found on the periodic table for each element. You will notice in this element box, there's two important numbers that we're looking at today. The number that is the whole number is, of course, the atomic number, and this represents the number of protons in the nucleus. The number up here is not the mass number. The mass number would be the number of protons and neutrons in a single atom of a particular element. But this right here can't be a whole, this is not a whole number. This is not representative of the count of protons plus neutrons in a nucleus. So this number here represents an average of all the isotopes of an atom, of an element that exists on the planet. And isotopes, of course, being the different versions of an element. Different versions of silicon would be that what they all have in common is 14 protons, but individual atoms of silicon might have a mass of 28, or they might have a mass of 29, or they might have a mass of 27, right? So isotopes, as you recall, are when you have different versions of the same element because they have the same number of protons, but they differ in how many neutrons and the individual atoms contain in their nuclei. So this number here, like I said, is not the mass number, it is atomic mass. It is an average of all those isotopic masses. And so let's figure out how we're going to average it, because it's not actually a straight average. So the term average atomic mass is a weighted average. It is not a straight average, and it's therefore going to be calculated differently from a normal straight average. So let's talk about what that even means, a straight average. A straight average is calculated by adding all the values in a data set and then dividing by the number of values in that data set. So, okay, that's a definition, but let's take a look at an example. Let's say a student has an 87% quiz average, a 73% test average, and a 92% lab average. If we were to do a straight average of all three of these grades, it looks something like this. Okay, and you should definitely, we're going to want a calculator out to do this, so if you don't, you should get your calculator out and do the problems with me. Okay, so a straight average is we're going to add up the values in the data set, the values being these three numbers. So 87 plus 73 plus 92. That's going to add up to something that we'll figure out in a minute. And we're going to divide by the number of values in the data set. There's 1, 2, 3, 3 numbers in the data set. And let's go ahead and put this into our calculator. All right, so 87 plus 73 plus 92, nope, 87 plus 73 plus 92 equals 412. We're going to divide that by 3, and okay, goofing up here. 87 plus 73 plus 92 equals, divided by 3. This is much better. Okay, so the straight average here is 84. Okay, so that's what we consider a straight average. What this means is that all three of these numbers have equal importance to the overall average. But sometimes we don't want each of those numbers to have equal importance reflected in the final average, and that is what a weighted average is. It's an average of a data set that recognizes that certain numbers as more significant or more important than others. So how we go about taking a weighted average is, first thing we're going to do is we're going to organize the data into some sort of table or some sort of organized rows and columns. We are going to convert the percent weights into a decimal, and to do that we're going to divide by 100. We are then going to multiply each data point by that decimal weight to get a temporary value. And then we are going to add up the temporary values to get the final weighted average. So here we have the same three numbers in our data set: 87 quiz average, 73 test average, 92 lab average. And then we also see here that this teacher doesn't want all three of these categories to have equal importance to the overall average. This teacher wants tests to be 65, to reflect 65% of the actual average, quizzes only 15%, and labs 20%. So the first thing that we have to do is organize the data into the data table. That's sort of been done for you. The next thing we're going to do is convert the percent weights into a decimal by dividing by 100. So these are our percent weights. We're going to divide each one of these by 100, and I'm going to put those here. I'm going to make this blank column. This is what I'm going to call the decimal weight. The decimal weight is just the percent value, the percentage, divided by 100, and it puts it into a decimal form, right? And so if you're not convinced about that, 15 divided by 100 is indeed 0.15. So dividing by 100 is just moving the decimal 2 places to the left. So our second percentage is going to be 0.65 as a decimal weight, and 20% is 0.20 as a decimal weight. Okay. We're then going to multiply each data point by the decimal weight, and we're going to put that in the temporary value column. So I'm going to multiply each number in the data set times the decimal weight, and I'm going to put that answer over here in the temporary value column. Okay, so we're going to have 87 times 0.15, and we're going to get 13.05. We are then going to take 73, and we are going to multiply by 0.65, and we are going to get 47.45. Lastly, I'm going to take 92, I'm going to multiply by 0.2, and I'm going to get 18.4, and I'm going to keep a 0 on there to keep everything to 2 decimal places. If I add now, the last step is to add up all the temporary values. So 18.4 plus 47.45 plus 13.05, and we are going to get a 78.90. So this right here is the weighted average for this particular student. So in this particular case, the student's weighted average is about a 79, if we round that up to about 79. A straight average for the student made this person's grade an 84, right? And so what we see here is that because the majority of the average is meant to come from the test average, and that test average for the student was lower than the other two numbers, that's what brings the average down closer to that 73 than the 84. Okay, so that's how a weighted average works. Just like your grades in this class are weighted, that's how those numbers are calculated. All right, so let's see how this works with atomic mass and isotopes. So the first kind of problem I'm going to show you is when only mass numbers are given for each isotope. When only mass numbers are given, we're just going to use that mass. So what we have here is a list of 3 isotopes: iodine 127, iodine 126, iodine 128. This number here that is written after the element name is the mass number. And remember, mass number is protons plus neutrons. Okay. And they're not actually telling us the actual mass of these, because the actual mass of each isotope is not exactly 127. It might be 126.98 or something very close to 127, but there's usually a little variation in the actual mass of each one of these. But in these cases, I'm not giving you the actual masses. I'm giving you only the mass numbers. So when only mass numbers are given to you, then we're going to just use that mass number for the isotope mass. So simple. The mass of iodine 127 is 127. The mass of iodine 126 is 126. And 128 is the mass for iodine 128. Okay. The percent abundances are given. Remember, what we need to do is divide each one of these by 100 to put it into decimal form. And I'm going to put that decimal form to the left because that's going to make my math visually simpler to look at. So 80 divided by 100 is 0.80. 17 divided by 100 is 0.17. And 3 divided by 100, be careful here, it is 0.03. All right, so remember, this is our decimal weight. Now what we're going to do is we're going to take each mass and multiply it by its decimal weight. And we're going to put those answers into the temporary value column. So we've got 127 times 0.8. And that first line looks like it works out to be 101.6. Our next number is 126 times 0.17. We get 21.42. Last line, 128 times 0.03. And we get 3.84. The last thing you do, add up these numbers. So 3.84, I already have it in my calculator, 3.84 plus 21.42 plus 101.6. So 126.86. Now, the mass, this right here is our average atomic mass. The unit is AMUs, atomic mass units. And here's what I want you to recognize. When you calculate atomic masses through this method, this was iodine. This number should match or very closely match the atomic mass on the periodic table. So let's verify that. So this was for the element iodine. So when we find iodine on the periodic table, we look at the mass number, or the atomic mass. Let me get that focused a little better. And we see here that it is 126.904. Very close to this number. Why is it not exact? It is very likely that these percentages are not perfectly 80% or 17% or 3%. These are probably rounded numbers, and we certainly knew that these were rounded numbers. So these problems are really wonderful because you can check your work on the periodic table. Okay, so let's take a look at this next problem. We have 4 isotopes of lead. Lead is the symbol Pb. We have a data table to organize everything already, which is nice. The chart's already been set up for us. We have 4 different isotopes, and we are being shown the nucleons. The nucleons are protons and neutrons in the nucleus. We know they are all lead. 82 protons. If we go to the periodic table, atomic number 82 is lead. So these are all lead. So here's the problem. We can't just call them lead because they're slightly different, right? We need some way to distinguish the fact that these are different from one another. And if you recall, when we go to write an element name, remember the number that comes after the element name is the mass number. And the mass number is protons plus neutrons. So this number here is not going to be 124 because that's only the neutrons. We need to add these up, 82 plus 124 is 206. Okay, we got 200 and, is that right? Oh, this is a typo. This is a typo. It's 122. You see that the same here. So this one's supposed to be 122. So that makes this lead 204. The next one, 82 plus 124 is going to be 2 more neutrons than the previous one, so this is lead 206. The next one has 1 more neutron than the previous one, so that's lead 207. And 1 more neutron yet is going to make this lead 208. Okay, so we got our isotope names. We know what the mass numbers are. Remember, that's the mass number. They are not giving us any more specific information about the mass of each one of these, so we will use the mass number as the isotope mass. So 204, 206, 207, and 208. Now we have to convert our percent abundances into decimal form, and remember, decimal form is you're dividing by 100, which just means you're moving the decimal 2 places to the left. Be careful on this first one. The decimal is going to be 0.0137. Next one down is going to be 0.2626. The third one down is 0.2082. And lastly, 0.5155. We then take the mass and multiply it by the decimal weight. My numbers are a little crammed. And we put those answers to each line into the temporary value column. So let's take a look and see what that looks like. We've got 204 times 0.0137. And that gives us a temporary value. I'm going to round that to the nearest hundredth, so 2.79. Next line, 206 times 0.2626. We get here 54.10, because I'm going to round it to the nearest hundredth. The third line, 207 times 0.2082. And I'm going to get 43.01. Yep, 43.01. And lastly, 208 times 0.5155. And I'm going to get 107.22. Temporary values. Notice that you're going to add all of those 4 numbers up. I'm going to start, since I rounded these numbers, I am going to start with a fresh calculator. 2.79 plus 54.10 plus 43.01 plus 107.22 equals. That gives me an answer of 207.21. The unit here is AMUs, and that is our average atomic mass for lead. If we go back to the periodic table, we will notice that the atomic mass listed on the periodic table for lead is indeed 207.2. We got 207.21, so pretty spot on. That's a really good check. All right, so let's take a look at some problems. This is part B, where I am going to give you specific masses for the individual isotopes. And we're going to use those specific masses instead of the mass number. So I've got a chart here, and I see that I have isotope with a mass number of copper 63, and I've got an isotope of copper 65. So let's go back up to the problem to get some more specific information. Element copper has 2 naturally occurring isotopes, copper 63, which has a mass of 62.93 AMUs, and it accounts for 69.2% of all the isotopes of copper. Copper 65 has an atomic mass of 64.93 AMUs, and it accounts for 30.8% of essentially the rest of the isotopes. Okay, so we are going to use these numbers in our mass calculations, not the rounded numbers. If I give you the specific information, you should use it. All right, converting percent abundance into decimal form and dividing by 100. We have 0.692 and we have 0.308. Okay, now we are going to multiply the masses times the percent abundances and put those values into the temporary value column. Okay, so we're going to have 62.93. 62.93 times 0.692, and we have a number, oops, the glare there, so 43.55. The next line, 64.93 times 0.308, and 19.998 actually rounds to 20.00. Let's add those up. What we have here is the average atomic mass for copper is 63.55 AMUs. When we find copper on the periodic table, we see that the mass here is listed as 63.546. So again, our calculations are very valid because the final answer matches the atomic mass on the periodic table. All right, in the previous three problems, you can see that we've organized the data for you already. Here's a problem where a chart's not been provided, and so it is your turn to create the chart. Okay. Typically, what works well is if you have a column that is where you write the isotope name. So isotope name, another column where you write the isotope mass. Give a column for percent abundance, and then you have a column for your temporary value. Okay, let's see what we've got. In this problem, we are looking at the average atomic mass of bromine. Bromine is the symbol Br. One isotope of bromine has an atomic mass of 78.92 and a percent abundance of 50.69. So I'm going to put that 50.69 here in this first line. The name of this is bromine, and it has a mass of 78.92 AMU. This isotope name, since this number is very close to the whole number of 79, this is bromine 79. It has a mass number of 79. The other major isotope of bromine has an atomic mass of 80.92. So this is bromine 81. Its percent abundance is 49.31%. Okay. So now remember, we're going to put those percent abundances into decimal form, 0.5069. And 49.31% becomes 0.4931. And now we have our two lines of multiplication where our answers are going to come over here to the temporary value column. That's 78.92 times 0.5069. And that works out to be 40.00. That's pretty amazing. Our next line, 80.92 times 0.4931. Let's try that again. 80.92 times 0.4931. And we are going to get 39.90. It's interesting, this problem. The percent abundances are about 50-50, so doing a straight average on these two probably would have given you pretty even or pretty similar results. Remember, you're adding the temporary values, and so you can see here you're going to get 79.90 AMUs as the average atomic mass for bromine. Verifying that on the periodic table, we see indeed 79.904. So our final answers here are remarkably similar. All right, this concludes our video lesson about how you find weighted atomic mass or weighted averages for isotopes. The average atomic mass is a weighted average, and the mass that you see on the periodic table, what we call the atomic mass, that number is representative of a weighted average mass of all the isotopes of that element that exists on the planet. All right, thanks for being here, and we'll see you back in the classroom.